complete the merge operation. Yeah, so this, divide conquer thing, very easy to understand. Next, let me use a diagram to show the details of the merge step. Actually, we did similar things in our homework assignment. Last two questions, we did similar things. All right, and here, these two subarrays are ordered already. So the first time when we do our first comparison, we compare their leftmost two elements in order, in their natural order from left to right. After first comparison, you can see the smaller one, here I use min 0, represent the smaller element in these two leftmost elements will be the global minimum, right? Global minimum. Yeah. So that global minimum element, we know it is the first element in the destination array, right? Yeah. So here, in this destination array, we can put it in place immediately. Yeah. So after the first comparison, we can put one element in place. All right. Then the larger one, this is the larger one. Here, just show you the idea. If the larger one is this B0, then our next comparison, we compare B0 with A1. That's our second comparison. Then we have a smaller one and a larger one. Smaller one, we know we can put it in place immediately. So after each comparison, we can put one element in place. The remaining element, then we do the next comparison, and so on. In natural order. In that way, at the end, we can merge all the elements to get a whole ordered array. Pretty straightforward. Pretty straightforward. All right. Is that the best way or not? So that's another question. Okay. Is this way optimal? Sorting algorithm? Is this merge step optimal? I don't know the answer. I only know it is very close to the optimal. May not be the optimal one, but very close to the optimal one. So we will see that later. That question, how to answer that question, optimal or not, how to answer, but very close to. All right. So in this way, but now we want to look at the worst case. When we merge two sorted arrays, we want to see how many comparisons do we need for the worst case. All right. Maximum number of comparisons we need for the worst case. All right. Every time, every comparison, we put one element in place. How many elements do we need to put in place? The maximum number of elements we need to put in place, because the last element when we work on the last element, we don't need any comparison, because that is the only element that left. So we can drop it in place without any comparison. So the last element we do not count, because we don't need any comparison to put it in place. Other than that, all the other elements, other than the last one, that's the maximum number of comparisons we need to put in place with comparisons. Yeah. All right? Yeah. So that's the number of elements except the last one. That number. Okay? Yeah. All right. Yeah. So, because you need to, yeah. So here, you need to do comparisons one by one to put element in place. Yeah. When you reach the second to last one, you still need to do one comparison. That's the worst case. Because for some other cases, if it's not the worst case, then somewhere, yeah, at some earlier positions, you already, after you put it in place, the remaining elements, you do not need any comparison. You can put them in place directly. Okay? Yeah. For example, yeah. So you consumed these elements. The remaining elements are all elements in one of the two subarrays. Yeah. All in B subarray or all in A subarray, then the remaining, you don't need a comparison, right? Because you know they are ordered, you can put them in place directly. Yeah. So that's not the worst case. Not the worst case, you are pushed to the last element in the subarray. Yeah. The last element in each subarray, you still need one comparisons to put it in place. That's the worst case. Okay? Yeah. So the answer for the worst case, now we can see 2k plus 1. The first subarray, you have k elements. Second subarray, you have also k elements. Total number of elements in these two subarrays, 2k, but you do not count the last element in place. So that's why you only count 2k minus 1. That's the worst case. Yeah. But this worst case, you assume both subarrays, both ordered subarrays, have the same size k. Yeah. Yeah. This assumption we can remove. Yeah. So next one, we look at the general merge set. So we remove that assumption. The first array, subarray, ordered subarray, there are n elements. The second ordered array, there are n elements. M and n, in general, they are different. So when they are different, when we do the merge, we have the similar result. So that is for the worst case. The total number comparison equals the total number of elements minus 1. M plus n minus 1. So this formula is for the worst case. Not the best case. Best case is different. Next, let's look at the best case formula. For the best case, now we have better understanding. So we know how to get a minimum number of comparisons. So we want to find a special input data such that we only need to do the minimum number of comparisons. So our strategy, so here you can see, so our strategy, so we try to exhaust one of the two subarrays as early as possible. All right? So here you can imagine, when you use the first element in one of the two subarrays to compare with the elements in the other ordered subarray, this first one beats all the elements in the other subarray. So you exhaust all of them as early as possible. After that, then all the remaining elements you can put them in place without comparisons. Because remaining, you know the order of the remaining elements. You don't need any comparison to put them in place. All right, so that's one case. Another one is the element, the first element in the first order subarray, when you do comparisons, it beats all the elements in the other ordered subarray. So that's another case you need to consider. It depends on which subarray is longer, which subarray is shorter. And you want to have, for the best case, you want to make the smallest element in the longer subarray to beat all the elements in the shorter subarray. That's the minimum number of comparisons. So in that situation, so your best case scenario, you need to exhaust the shorter array. So the formula is the minimum of m and n. The minimum of m and n, that's the best case formula. So these two formulas. When we do the merge, so one best case, one worst case. Then the remaining cases somewhere in the middle, between these two numbers. All right. Then C.3, efficiency analysis for Mergesort. So now we can estimate. So this efficiency, we need to do estimate. All right. Because to get an accurate formula, very hard. So we don't want to do very accurate calculation. So we do some estimate. Good enough. All right. Derive recurrence relation. All right. When we count the number of comparisons for the Mergesort, we want to use a recurrence relation for that counting number function. All right. Estimate the worst case. For the worst case, what is the worst case? Worst case, each merge, we use the worst case, right? Worst case formula. Each merge, we use the worst case formula. The number of comparisons. Let this capital T function, number of comparisons. All right. So then we make even split. Each subarray, about half of the data size. So here we use T of n over 2. Here we do, a rough estimate. So we we do not need to make accurate, n over 2 take floor function, ceiling function, right? That's too complicated. Here, so that's roughly, we use the data size n over 2. So that's the data size. Yeah. Although it may not be integer, but we just want to, because it's close to an integer, so we just want to make a close estimate. All right. Yeah. When we do the merge and comparisons, another approximation, because you may argue n minus 1, right? Total number of elements minus 1. Yeah. So that's the exact formula, but we make it as simple as possible, so we use n as a simple estimate, approximation. So then our recurrence relation becomes the simple recurrence relation. Two base cases. One element, no comparison. Two elements, one comparison. Two base cases. Then the remaining T of n, in order to do the merge sort on an array with n elements, so you need to split, to even split. Each subarray, the size is approximately n over 2, and when you do the merge, you need to do n comparisons. So you get this recurrence relation. Now we want to estimate this capital T function. When we do the estimate, here we use a special way to do the estimate. All right. First, we consider simpler case. Simpler case, n is power of 2. That's the simplest case. N is power of 2. Okay? Yeah. Then all our recurrence relations, we have good numbers. Division by 2, we always have good numbers. Okay? All right. Yeah. Then we need to do a special operation to make the formula more friendly, to make the formula expose the structure clearly. Yeah. So what kind of division method here? So what kind of division? Division by 2 to the k. Yeah. Do this division method. Yeah. Because after this transformation, we can see a special structure here. This ratio, look at the ratio structure, similar structure at both sides of the equality. That structure, ratio structure, we use a new function to represent it. Yeah. Same structure, but with different parameter, right? Yeah. K and k minus 1, different parameter. Yeah. So we define a new function to see this recurrence relation better. Now, what's the new function? A capital G function, G of k equals this ratio. Why you need to introduce this G function? Because after we replace this special structure with a single G function, we can see we can see things better, right? Yeah. So your new recurrence relation much simpler, this G function. After substitution, your new recurrence relation becomes much simpler. Then you can do iterations directly. Yeah. Yeah. Definitely, we need to have the base case. Base case. Plug in. Okay. When k equals 1, yeah. If k equals 1, we plug in. Okay, yeah, G of 1. Yeah. All right. Then, so iteration. Next slide. Kills me. Let me drink some water. All right. Keep going. Then, invariant concept, right? Remember? How do we keep track of the data? Here we have that issue. Keep track of the data. Invariant. The concept. The parameter k minus 1 plus this 1 equals k. The parameter k minus 2 plus this 2 equals k. That's a constant. The same for all these equations. Size plus that constant. Yeah. All right. So when we get to the bottom, so when the parameter becomes 1, then that constant becomes k minus 1. Yeah. G of 1, we know 1/2. Okay, so we plug in, yeah, k minus 1/2. Yeah. Now we get back to the t function. Yeah, t function. Yeah. And we use n. 2 to the k, that's n. Yeah. That's n. So we get this expression. Yeah. K, that's log base 2 of n. Right? So when n equals 2 to the k equals log base 2 of n. So you get an estimate of t of n approximately equal to n times log base 2 of n. Okay? But that's the simplest n structure, power of 2 structure. We have this formula. But for the general case, no. So we need to go to the general case. Yeah. All right. So for the general case, yeah, so here, yeah, so already at this point, at this place, so we, yeah, so we, you know, yeah, here I finished this discussion, but I want to talk about the general case. The general case, there is a method. We call recursion tree method. Recursion tree method. Okay, all right. Yeah, because this recursion, we can draw a tree. Each node corresponds to the current t function evaluation. Binary tree, yeah, because you have 2 branches. Yeah. Binary trees. Every time when we split, yeah, you know, so we get a binary tree, that recursion tree. Using that recurrent tree, we can estimate the general cost. The general cost. Okay, all right. Yeah. The general cost, we can estimate the final formula, still n log n, yeah, easily. Yeah. But that way, yeah, because in our module 2, we will do similar analysis in module 2. Not module 2, part D, in our last part of module 4, that's part D. We will do efficiency analysis with similar recurrence relation like this. So at that time, I will draw the recursion tree to show you how to estimate. Yeah. All right. So that's one thing. Yeah. So in that way, we only need to do it once. We can save some time. Yeah. Similar idea. Yeah. All right. So that's one. another thing, yeah, because that's for the worst case, right? Yeah. So this formula is for the worst case. Yeah. But you may ask, how about the best case? So for the merge operation, at each merge step, we want to apply the best case formula, not worst case formula. Best case formula, the minimum of n and n, this formula, but remember we do even split. So the sizes of two subarrays, we can use the same size. But that size is 1/2 of the n, right? Yeah. That means for the best case, we just replace this n by 1/2 of n. 1/2 of n. Then you can see, yeah. So your difference is only the constant. The main part is still n log n, but your constant is different. Yeah. So your constant is different. You still get n log n, but the constant is different. Yeah. Just the 1/2 constant. Yeah. Why 1/2? Yeah. Because later when we use the recursion tree method, that 1/2 is carried over, yeah, everywhere, 1/2. Yeah. So when you calculate the total cost, total recursion cost, yeah, because the difference is only you multiply by that 1/2. Yeah. So the best case, yeah, approximately 1/2 of the worst case. Yeah. Yeah. All right? Yeah? So still in the same category. Yeah. So for the merge sort, best case, worst case, in the same category. All right. Then, what's the benefit for the merge sort? What is the benefit for the merge sort? What is the advantage of the merge sort? The advantage is, this is its advantage. Its worst case is controlled to, its worst case is controlled to big O of n log n. That's the advantage of the merge sort. For other sorts, we have learned at this point, worst case, big O of n squared. Selection sort, bubble sort, insertion sort. Then next class on Wednesday, we will learn quick sort. Quick sort, worst case, also big O of n squared. Now, most sorts, not all, most of the other sorts, worst case, big O of n squared. Now you can see, worst case has this advantage. Worst case in big O of n log n, that means it avoids poor worst case. Based on the way we do divide and conquer, because we use the most balanced data split way. When we do data split, we use the most balanced data split way. So that's the reason we can control the poor performance of the worst case. Avoid the bottleneck. Worst case is the bottleneck. Here we can reduce the impact of that bottleneck problem. Sometimes it could be useful, but sometimes people may not care about that bottleneck. But it has this advantage. Okay, all right. Yeah. So that's the Mergesort. Yeah. Next, I want to talk about, last time I gave you the formula, but I didn't explain the formula. Yeah. But I want to use the remaining time. I want to, try my best to explain that formula, to make you feel better. Yeah, because some students may wonder, how do you get this formula, right? Yeah. All right. So that is the decision tree method. Yeah. I want to introduce this decision tree method. Yeah. A powerful method. Yeah. For that lower bound formula, remember I gave you a lower bound for n element sort, comparison-based sorts for n element. That's the seeding function of log base 2 of n factorial, this lower bound formula. How to derive this formula? Yeah. So I want to use the remaining 20-something minutes to show you the main idea, the method, decision tree method. Yeah. Not recursion tree, but decision tree this time. A different thing. Yeah. All right. So this method is, in analysis, is very powerful. Yeah. All right. Idea is very simple. Yeah. So let me show you the basic idea. What is the decision tree? All right. Here. The basic theory of the decision tree, very simple. Decision tree idea. Approach method. All right. So we want to model the comparison operation. Model. Okay. So here. Model the comparison operation. How to model? Yeah. Yeah. So what do we model here? Yeah. We just represent comparison in a different way, in a visual way. All right? Yeah. So here, decision tree, because you see a tree, right? Yeah. So this part, so we do some visual understanding. Visual understanding. All right? Yeah. All right. How do we model? Because in a tree, the basic construct in a tree is a node, right? Yeah. So there is a node. Node in the tree. Okay? All right. This node corresponds to one comparison. One node corresponds to one comparison. All right. Yeah. Then, when you do comparison, we interpret it. We interpret a comparison as a decision-making process. Okay? All right? So here, let's compare two elements. X and Y. Okay? Here, I use this colon to separate. X and Y, we do comparison. When we do comparison, we interpret it as we make a decision. Yeah. Because comparison, you have results, right? Yeah. So you have different outcomes. Yeah. That corresponds to the decision-making process. All right. Yeah. So two branches from this, because we want to draw a binary tree. Yeah. Binary tree, more convenient. So when we make a decision, we have two possible outcomes, so we can use the binary tree to represent comparison results. Yeah. All right. Yeah. Left branch corresponds to the case x less than or equal to y. Yeah. Right branch corresponds to x greater than y. Yeah. All right. Another note. Yeah. Then this node, the node, different places, we need to make another comparison, a different comparison. Yeah. It's a different comparison. So another decision. Yeah. Each node, yeah, we need to make that decision. Yeah. So then we draw decision tree. Okay, all right. Yeah. Yeah. To show you, the whole picture. Yeah. So here, let me use a simple example to show you the whole picture. So what's that example? Simple example. Sort a 3-element array. I use the decision tree method to sort. Okay? So you know how to sort. Yeah. But to help you understand this decision tree concept, now I use the decision tree way to do the sorting. Yeah. All right? Yeah. Decision tree, yeah, so let me use the 3 elements. ABC, how about that? ABC. 3 different elements. Yeah. All right. We have many different ways, right? Yeah, we have many different ways. All right. Yeah. First comparison, the root node. Root node corresponds to our first comparison. A:B, root node. Yeah. 2 branches. A less than or equal to B, and A greater than B. All right. For the left branch, yeah, so we get some information. Yeah. So what is our next comparison? Yeah. A, B, how about B:C? We compare B and C. Yeah. So then, 2 branches, left branch B less than or equal to C, right branch B greater than C. All right. But for this left branch, after 2 comparisons, we have the sorting result, right? Yeah. Because we know the order. Okay? Yeah. A less than or equal to B less than or equal to C. Yeah. So the result, I use this rectangular box representing the leaf node. It's a leaf node. So we can stop. Yeah. So that's our sorting result. All right. For this right branch, because we do not have the result, right? Yeah. So we need one more comparison. Yeah. We need to compare A and C and see which one is smaller, which one is larger. Left branch, A less than or equal to C. Right branch, A greater than C. Okay? Left branch, we get a sorting result. Yeah. A less than or equal to C, strictly less than B. Right? Yeah. This branch, C less than A, less than or equal to B, right? Yeah. Sorting result. Yeah. Then, this right branch, we can do similar things, right? Yeah. So I do not need to repeat. So you can see the whole picture pretty much well. Okay? Yeah. So it's enough for you to see the whole picture. Yeah. So this is the decision tree corresponds to one of the sorting algorithm for this computing problem. Because you may have different sorts, right? There are many different ways to sort a given 3-element array. Yeah. So your different sorts, you draw a different decision tree, right? Yeah. So your decision tree, another decision tree. Okay? All right. That's the background we need to derive that lower bound formula. So this is the background. Okay? All right. Now we are ready to derive the lower bound formula. All right. Yeah. Yeah. So let me move to the next screen. Yeah. All right. Because this time we need to consider the general case. All right. So our general question. Sort an element array by comparisons. So here I emphasize this comparison operation because we want to exclude non-comparison sorts, right? Yeah. So there exists some special sorts without relying on comparison operations. Yeah. So we want to exclude those sorts. So we only look at the comparison sorts. Yeah. People call the comparison sorts comparison-based sorts. In short, comparison sorts. Yeah. All right. Then we can draw decision trees. Here we need to draw a general decision tree. Yeah? So this time, so we need to draw a general decision tree. For any sort, right? Yeah. Arbitrary sort. If you can sort an element array, then use our decision tree method in describe it in the previous screen. We can draw its corresponding decision tree, right? No problem. We can draw because we follow step by step. What is your first comparison? What is your second comparison? What is the result of your first comparison? What is the result of your second comparison? If you can tell me all those decision results, then I can draw its corresponding decision tree without any question. So at the end, you will have the decision tree. We know it is a binary tree, right? It is a binary tree. So we know the structure of binary tree. All right. Now, we need to estimate. All right. First, let's draw a general binary tree. Node. All right. Node. All right. Yeah. Quite general. All right. Binary tree. Yeah. All right. Then, some important concepts. In this decision tree, what's the meaning of each leaf? Yeah. Each leaf corresponds to the result. sorting. Leaf, each result of sorting for one input, right? One input array. Each leaf. Yeah. Because if your input data is different, the order is different, then when you follow the decision tree branches, you will end up with different leaf node, right? So your destination will be a different leaf node. All right. So for one input array. Input array, actually, the main property that determines which leaf you end up with, so that's the specific order information. What is the specific order? Okay, all right. Yeah. N elements, yeah, because n elements, we need to represent n elements. Okay, yeah. X1, X2, Xn. All right. Then, for sorting result, we just arrange these n elements in a special way, right? Yeah. In the special way, can we treat, so in our arrangement, if the smallest element is the second element, can we use its subscript? Is good enough? We only need to store the subscripts of these elements, right? 5, 1, 7, and so on. N minus 2, yeah. You can see the specific order can be represented by, what's this? We know the concept, it's called a permutation, right? Permutation, so one permutation of n numbers, right? And consecutive integers, yeah. So n numbers, n, what is that? Yeah. Permutation. So you can see one sorting result corresponds to one permutation. So each leaf, in other words, each leaf can be represented by one permutation of n numbers. How about that? That kind of abstraction, that kind of interpretation, symbolic interpretation. All right. Then, how many permutations? How many number of total permutations? How many? Of n numbers. How many? Okay, all right. Is it n factorial? Is it n factorial? M total, n permutations, n factorial, right? Yeah. In discrete math, you learn this formula, okay? The number of permutations with n different symbols, that number is n factorial. Yeah. Here we use that formula. All right. Now, that means the number of leaves, based on that, number of leaves of the decision tree, number of leaves is greater or equal to n factorial. Yeah. Number of leaves, we can use capital L to represent. So capital L is greater or equal to n factorial. Yeah. Why is that? Why greater or equal to? You understand equal, right? The equal case, yeah? So capital L equals n factorial, but there are some cases that capital L strictly greater than n factorial. What's that? Yeah. Remember, when we apply decision trees on arbitrary algorithm, arbitrary sort on n element array, some algorithms could be very bad, right? Yeah. So we also cover those bad algorithms. Bad algorithm means you have a lot of redundant comparisons. You do a lot of redundant comparisons. Okay? You waste some of the comparisons. When you do redundant comparisons, when you draw, your decision tree should be larger, right? Your decision tree should have more nodes. In that case, the number of leaves could be strictly greater than n factorial. Because some of the leaf nodes are wasteful. You don't need those leaf nodes. So we include those bad algorithms. Yeah. All right, so we have this. All right. Another thing, worst case. Our goal, we want to estimate the worst case. Worst case. The number of comparisons for the worst case. Yeah. So in this decision tree, can you see what's the number of comparisons for the worst case? So we want to see it in the diagram. Yeah. So let me refer to the previous slide. Yeah. So in this example, so what's the worst case? Worst case, you need 3 comparisons, right? 3 comparisons. So this path corresponds to the worst case. Each edge, 1 comparison, 1 comparison, 1 comparison, 1 comparison. Each edge represents 1 comparison. So, these paths, 3 edges, but this path, 2 edges. So that's the best case. So worst case corresponds to the longest path. Yeah. So here we know the longest path from the root to a leaf. Yeah. One of the leaf node. Just longest. All right. That's the worst case. Okay? All right. That's worst. And this longest path, the length. Okay? So, yeah, because we only need to use the length. The length, we have a concept called height. That's the definition of the height of this tree. Okay? All right. So now for the worst case, when we estimate the worst case, yeah, we just, here let's use little h represent the height. Okay? Height. We know that's for the worst case. Worst case. All right? Height. Yeah. All right. Now we move to our current slide, second slide. Now we want to estimate H. Yeah. So there is a formula. Okay, all right. Capital L less than or equal to 2 to the H. There is this inequality. So why is that? Yeah. Here, yeah. How to see this inequality? Yeah. It's very easy. Yeah. So we consider a complete binary tree. Complete binary tree. So you know what is a complete binary tree. Okay? All right. All levels are full, right? All levels are full. Complete binary tree. Complete binary. For complete binary tree, there is this one. Capital L equals 2 to the H. Yeah? Capital L, number of nodes at the bottom level. Yeah, because the height is H. Yeah. All right. So when you reach the bottom is full. When the bottom is full, you have capital L equals 2 to the H. Now, the general decision tree, not complete, right? Yeah. Not complete. That means the number of leaves becomes smaller. Yeah. Yeah, because some of the branches you do not grow to the bottom level. So some of the branches shorter. Yeah. Because each node, when you go from current level to next level, one node you split to 2. One split to, you increase the, before the split you have 1 leaf, right? After split you have 2 leaves. That means when you do as much split as possible, you grow the number of leaves. And the complete binary tree, you do the maximum number of splits. Maximum splits. That means that's the largest possible leaves you can have. Okay? All right. The largest possible leaf, that's 2 to the H. Okay? All right. Then, capital L greater or equal to n factorial. Yeah. Then, you solve this formula. Is it H greater or equal to log base 2 of n factorial? H is an integer. Can we put a ceiling function on it? So we derive this capital little h, not little h greater or equal to ceiling function of log base 2 of n factorial. And we know little h means the worst case number of comparisons. Yeah. So that's why it's the lower bound. This formula gives us the lower bound. Yeah. All right. Yeah. So I complete explaining this formula. Yeah. All right. So that's it for this class. Next time on Wednesday, we will start part D of module 4. So you need to, so tomorrow you will see 2 assignments. One, programming project number 2. Another is our homework assignment number 2. Yeah. All right. Yeah, that's it.